This lecture is about multivariate processes. In many applications, you measure several data sources simultaneously. For instance, in radio astronomy, you measure using different radio telescopes from different locations so that you can get a high-quality image of the sky. Similarly, you can estimate for mobile base stations. You have multiple antennas receiving the telecommunications channel from the mobile phone, and in this way allowing the antenna to focus on a particular user with many antennas so you get a better gain for that person. This is a way to handle fading channels, for instance, where you have local areas where you have poor signal. By combining the signals from many antennas using their spatial distribution, you are able then to improve the communication. To be able to model this kind of signals, we introduced the notion of an m-dimensional stochastic process. Essentially, this is just a measurement containing m different measurements that you concatenate, saying that all of these m measurements were gathered at the same time or same space, location, or whatever you have as dimensions for your measurements. Think of it as a measurement in time, where the m different sensors are located at m different places. But there can, of course, be m different shares, and you want to find combined structures between them. They're just m different signal sources that you wish to model jointly. To compute the mean of such a process, you basically just move the mean inside the vector like this. The covariance function is now a matrix function, so that means that each covariance lag, before that was just a number, but now this is a matrix. However, I still retain the same conjugate symmetry that I had for the covariance function. For a white noise, now there is a difference that we have a whiteness in time, temporal whiteness, as well as in space. If the process is temporally white, meaning that it is a white sequence in the traditional sense as we observed before, we have this form of a white noise. That's the standard definition of it. If you also impose that it should be what we call temporally and spatially white, if we assume that the second dimension is space in this case, you say that also that the covariance in between the sensors are also white, so they are not correlated with each other either. We call such a process a doubly white process. So for instance, in the example of the telecom, you typically have the thermal noise, the background noise, as being assumed to be doubly white, meaning that for each of the different sensors you assume that you have a white noise that is not related to the measurement you have at the other sensors. We can of course extend the notion of an Armax process in the same way. We are just introducing then a matrix polynomial for the A and the B and the C and so forth. So everything is just the same thing as it was before, except that now instead of a 1, this is an identity matrix. Instead of an A1 coefficient, this is now an A1 matrix, and so forth. To ensure stability, we now require that all the roots of the determinant of A set to 0 are all inside the unit circle. This is the same thing as required that the A polynomial had their roots inside the unit circle in Z before. Of course, I can exclude parts and have a VMA, vector MA, a vector AR, varma, and so forth, depending on which part I include. So basically all the standard definitions of the process follow, except that now my coefficients are matrices. Let's look at an example. This is a first order MA, or a vector MA now, since it is multi-channel. Since it's an MA1, I have a C polynomial looking like this. If I form the covariance sequence, I get this, and you can see here, note in particular, that the lag goes to 0 as soon as I pass the order. I have to treat the diff k of k is equal to 1 and k is equal to minus 1 differently because of the matrix multiplication order, but everything basically looks the same otherwise. Oh, there's some missing parentheses here. If I similarly look for a vector AR, a var process, I have an A polynomial looking like that. I assume then that the determinant of this evaluated over Z have its roots inside the unit circle. And if I compute it, I will get the corresponding Joule-Walker equations looking like this. Clearly, these are not going to 0, just as in the univariate case. Rather, they exhibit the same form of ringing behavior that we expect. If I use this equation and move this part over to the other side, I can express the covariance matrix of the noise this way. Using the second equation, I can replace Ry minus 1 and I'll get this expression here, which is then just a compact way of writing the covariance matrix of the noise, given the A coefficients and the variance of the process. I can form the autocorrelation matrix in the similar way. Notice again that the ACF here is a function of matrices indices, so each index in my ACF is a matrix. I form that by scaling, and then to scale it, I will then scale, instead of dividing by R of 0 as I did before, I will need to scale each index using a diagonal matrix formed like this. Here the mmth component is the same thing as saying that I take the matrix Rz of 0 and take the mmth element in that. So this would be the mmth element. Here's an example of what an ACF can look like. Notice that they are matrices. Here's like 1, like 2, like 3, like 4, like this. What you typically do is that you compare it to the confidence interval that you have, and then just dictate below the confidence interval or above the confidence interval. So if it's below, I'll just say a minus. If it's above, I'll just say a plus. And then if it's inside, I'll just make a dot like this. In this way, I can more easily see whether something is deemed to be outside the confidence interval or inside. You can compute the PACF by using the multivariate Joule-Walker equations. And then, of course, you can use the ACF and the PACF in a similar way as in the univariate model to identify identify if it's an AR, an ARMA, or an MA structure is suitable to describe the data you have observed. Working with multivariate processes, you very often use the Kronecker product to simplify your equations. And the trick you then use is this one. Here I'll take the vec of the matrix A, B, and C, and I'll rewrite it as C Kronecker product A vec B. And of course, to be able to say what that means, we have to clarify what the vec operation is. And basically, the only thing the vec operation does is that it stacks column vectors on top of each other, like this. So the vec operation just vectorizes a matrix by stacking the columns on top of each other. The Kronecker product, on the other hand, works like this. Notice that I take 1 times this matrix, and I'll place it here. Then I take 2 times this matrix, and I'll place that here. 3 times this matrix, and I'll place it here. And 4 ends up here. So the Kronecker product allows me to express a large matrix more compactly. That means that if I use the expression I had before for the covariance matrix, I can use the vec operation to describe it like this, where the A bar now denotes the conjugate. This can vastly simplify my calculations. Here's an example of that. So say that I have a first order vector AR process with an identity matrix as the covariance matrix of the driving noise. So this is a doubly white process. This is my A coefficient. And first thing I do is I check if the determinant has its roots inside the unit circle. And as you can see, the roots in Z, not in Z minus 1 again, this is its roots in Z, they are inside the unit circle, therefore the process is stable. If I denote the covariance matrix at lag 0 this way, I can set up the equation like this. This is just the equation I had on the previous page. Then what I can do is I can multiply these together, and I can identify what the R11 coefficient is and R12 coefficient is by just solving the set of linear equations that will result. This will be super tedious. Instead, I can use this vec operation and rewrite it like this. The vec of the sigma is this one, the vec of the covariance matrix is this one, and this product I can form like this. Notice I can very easily solve it by just computing the inverse of this matrix and multiply it on the other side, and I'll get the solution right away. Of course, I have to reorder it back to this form, but I have then solved it, and I have the covariance sequence like this. As expected, R12 is equal to R21. Remember, this is a conjugate symmetric matrix. You will find that anytime you work with multivariate processes, this kind of trick where you use the Kronecker product and the vec operation together simplifies your calculations quite a lot.